The universe you know is a ghost town built on invisible foundations. Over 99% of the cosmos is made of dark matter, a substance that weaves hidden structures governing everything we see. This journey uncovers 25 lost cosmic architectures, from ancient gravitational scaffolds to phantom voids, that dictate the flow of galaxies and the ultimate fate of the cosmos. By the end, your understanding of reality itself will be fundamentally reshaped. We will explore why entire superclusters move toward an unseen gravitational sinkhole, and what colossal walls of galaxies could reveal about the universe's infancy. What part of the hidden cosmos most captures your imagination? That faint, almost imperceptible whisper in the cosmos began with a quantum tremble. In the first fleeting fractions of a second after the Big Bang, the universe was a realm of pure energy, and within it, tiny, random fluctuations flickered in and out of existence. Then, a monumental event called inflation occurred, stretching space itself faster than the speed of light. This explosive expansion acted like a cosmic amplifier, taking those minuscule quantum whispers and magnifying them into the first permanent wrinkles in the fabric of reality. These wrinkles were slight overdensities, regions where there was just a tiny bit more stuff than in the areas around them, and that stuff was almost entirely dark matter. This was the birth of the primordial dark matter web, the first and most fundamental of our lost cosmic structures. Think of it as a ghostly skeleton, an invisible framework laid down before anything else existed. This was not a web of shining threads but of gravitational potential. The denser knots in this web exerted a stronger gravitational pull, acting like deep wells in the landscape of space-time. Ordinary matter, the protons and electrons that would eventually form us, was still a superheated, turbulent plasma, far too energetic to be held by these gentle gravitational tugs. But the dark matter, being cold and sluggish, felt the pull immediately and began to settle into this underlying architecture. It was the perfect scaffold, stable and patient, waiting for the universe to cool. The evidence for this ancient web comes from our most powerful supercomputers. Simulations like the famous Millennium Run take our best theories of physics and run them forward in time, recreating the entire evolution of the cosmos. They start with nothing but those initial quantum fluctuations and the laws of gravity. The result is always the same, a stunningly intricate, cosmic-scale network of dark matter filaments connecting at dense nodes, a structure that mirrors the actual distribution of galaxies we observe in the night sky with uncanny accuracy. This is how we know the web is real. We can watch it form in a virtual universe. The galaxies and brilliant stars we see are merely the tracers, the glittering lights strung along the invisible power lines of the dark matter grid. So what does this mean for our understanding of empty space? It shatters it. The void between galaxies is not empty at all. It is pervaded by this fossilized architecture, a relic from the universe's first moments. Every galaxy, including our own Milky Way, sits within a vast, diffuse halo of this primordial dark matter, a ghostly reminder of its birthplace within that ancient web. This foundational structure set the stage for everything to come, a cosmic destiny written in invisible ink. And as we peel back this first layer, we find it points toward an even more unsettling presence, a force that seems to be tearing the very fabric of that web apart. But that foundational dark matter web did more than just build galaxies, it set them in motion. Our entire Milky Way, along with its local galactic neighbors, is racing through space at a staggering 2 million kilometers per hour. For decades, astronomers were baffled by this motion. Where could such an immense velocity possibly come from? The answer lay in a direction toward the constellation Centaurus, a mysterious region they named the Great Attractor. Think of it as a gravitational sinkhole of cosmic proportions, a focal point pulling in everything around it. The core of this anomaly, however, remained a profound mystery, hidden from our view by the thick band of dust and stars that forms the plane of our own galaxy. This region is so obscured that astronomers call it the zone of avoidance because optical telescopes simply cannot see through it. It was like trying to map a mountain range while standing in a dense fog. The initial discovery came not from seeing the attractor, but from feeling its pull. By meticulously tracking the peculiar motions of thousands of galaxies, scientists like Alan Dressler and his colleagues in the 1980s realized they were all streaming toward the same invisible point. The gravitational tug was undeniable, suggesting a concentration of mass equivalent to tens of thousands of Milky Ways. But what was it? The breakthrough came when we learned to see with new eyes. Infrared and radio telescopes, which can penetrate the cosmic dust, finally peered into the zone of avoidance. What they revealed was not a single, monstrous object, but a supercluster of galaxies with a dense Norma cluster at its heart. This was the unseen core of the Great Attractor, a colossal knot in the cosmic web where the dark matter filaments converged into an overwhelming gravitational well. Its power comes not from a single dark overlord, but from the combined heft of thousands of galaxies and their immense shrouded halos of dark matter. It serves as a humbling reminder that some of the universe's most dominant structures can remain lost simply because of our own limited vantage point. What other gravitational giants might be hiding just behind the veil of the Milky Way, silently steering the flow of entire galactic families? The pursuit of the Great Attractor's core was a triumph of indirect discovery, but it also revealed something even more unsettling. Our entire local universe, including the Great Attractor itself, is being pulled towards something far more immense and distant. That immense pull towards something beyond the Great Attractor hints at a cosmic landscape far more textured than we ever believed. But what if the most defining structure in our local cosmos is defined not by what is there, but by what is not? We appear to be living inside a staggering emptiness, a billion light-year-wide bubble of relative nothingness known as the KBC Void. Named for astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, this is not a perfect vacuum, but a cosmic desert so vast and underdense that it challenges our most fundamental assumptions about the universe. While the Boötes Void is a famous example of cosmic emptiness, the KBC Void is far larger, and most unsettlingly, we are inside it. Galaxy count surveys have repeatedly shown that the density of galaxies and clusters in our immediate cosmic neighborhood is significantly lower than the universal average. It is as if we reside in a colossal, cleared-out cavern within the grand cosmic web. This presents a direct challenge to the cosmological principle, the long-held idea that on the largest scales, the universe is smooth and uniform, looking roughly the same everywhere. The KBC Void suggests that the cosmos might be more like a block of Swiss cheese with vast holes and dense clusters, rather than a perfectly risen loaf of bread. This void hierarchy, where smaller voids merge over time to form giants like the KBC, means that emptiness is an active, evolving component of the universe's architecture. Our position within this local desert has profound implications. Measurements of how fast the universe is expanding, known as the Hubble constant, can be subtly different inside a void compared to outside. The relative lack of gravitational pull from surrounding matter might make our local expansion measurements slightly faster than the true global value. This could be a key piece in resolving the ongoing tension in cosmology, where different methods of measuring the universe's expansion rate disagree. Some theorists, like Laura Mersini-Horton, have even proposed a more radical origin for such vast voids, that they could be imprints or scars from collisions with other universes in a wider multiverse. Whether from cosmic chance or a multiversal fingerprint, the KBC Void forces us to see emptiness not as a passive background, but as a dominant sculpting force. It is a lost structure defined by its absence, a silent, cavernous presence that reshapes our view from the inside out. And if we are living in one of the universe's great empty quarters, what immense matter-rich structures must lie waiting in the darkness beyond? Our cosmic address just got a major revision. We are not merely residents of the Virgo Supercluster, but citizens of a far grander continent of galaxies known as Laniakea, a Hawaiian word meaning immense heaven. This is the fourth lost structure, a gravitational metropolis whose true borders are not fixed in space, but are defined by the shared destiny of 100,000 galaxies all flowing in the same cosmic river. The team of astronomer R. Brent Tully did not map Laniakea by simply drawing circles around groups of galaxies. Instead, they charted the subtle motions of these star cities, tracing the paths they take as they are pulled by gravity. Imagine a vast, rolling landscape where every stream and river flows toward a single, central valley. Laniakea is that valley's watershed, a basin of attraction on a cosmic scale. Every galaxy within its domain, including our own Milky Way, is ultimately streaming toward the same gravitational focal point, the Great Attractor, which acts as the supercluster's dense, powerful heart. This means our home is not defined by where we are, but by where we are going. The architecture of Laniakea is a delicate web. It encompasses familiar clusters like our own local group, the massive Virgo cluster, and the Hydra-Centaurus complex, all tied together by faint, bridge-like filaments of dark matter where galaxies string like pearls on an invisible thread. Our Milky Way resides on a remote filament, a quiet suburb in this sprawling galactic empire. Yet this immense structure is temporary. The relentless expansion of the universe is constantly stretching these gravitational bonds. The filaments that connect the clusters are being drawn out, thinning over billions of years. The shared motion that defines Laniakea today will, in the far future, be overcome by the stretching of space itself. The continent will slowly dissolve, its member galaxies drifting apart on different cosmic currents. So what does it mean for our identity to be part of a structure that is fundamentally transient? Laniakea teaches us that the universe's grandest architectures are not monuments, but moments in a flowing, dynamic masterpiece. This raises a profound question about the very glue of the cosmos. What unseen force could possibly bind such fleeting empires together, and what could ultimately tear them apart? That flowing, dynamic masterpiece of Laniakea is just one thread in a tapestry of staggering scale. A wall of galaxies stretches across the cosmos, a structure so immense it challenges the very definition of what the universe should allow. This is the Sloan Great Wall, a filament of concentrated matter over 1.4 billion light-years long. Discovered in the early 2000s through the Sloan Digital Sky Survey, this was not a discovery made by looking at a photograph. It was an achievement of three-dimensional cartography, a patient mapping of the precise positions and distances of millions of galaxies. The resulting map revealed this colossal ribbon, a concentration of numerous galaxy clusters and groups all seemingly strung together, forming the largest known structure of its kind in the observable universe. It makes earlier discoveries like the CFA2 Great Wall seem almost local by comparison, showcasing how our vision has expanded with new technology. Astronomer J. Richard Gott III noted that such structures push the limits of what we thought was possible. The existence of the Sloan Great Wall is permitted by a process called gravitational instability. In the early universe, those slight overdensities in the dark matter web acted as seeds. Over billions of years, gravity relentlessly pulled more and more material, both dark and visible, into these regions. The Sloan Great Wall is the result of this process operating on a truly epic scale, a mountain range built by the slow, patient hand of gravity, yet its sheer size presents a puzzle. The cosmological principle suggests that on the largest scales, the universe should be smooth and homogeneous, like a vast, well-mixed batter. A structure as large as the Sloan Great Wall seems to test that principle, appearing as a genuine anomaly, a continent in an ocean that should only have islands. Is it the largest possible crest of a universal wave, or does it hint that our understanding of cosmic uniformity is incomplete? This monumental wall, for all its grandeur, is not eternal. The same dark energy that accelerates the expansion of the universe is acting upon it. Over cosmic time spans stretching trillions of years into the future, the gravitational glue holding the wall together will be overcome. The galaxies within it will be pulled apart, their connections severed by the stretching of space itself. The Sloan Great Wall represents a pinnacle of visible architecture, a temporary monument to gravity's power in a universe increasingly dominated by a mysterious repulsive force. If this is the largest structure we can see, what even grander, invisible frameworks of dark matter might be lurking just beyond our perception, dictating the placement of these glittering walls themselves? Even the most colossal walls of galaxies cannot account for a current that seems to pull the entire observable universe. Astronomers have detected a coherent stream, a mysterious drift of galaxy clusters all moving in the same direction at incredible speeds. This phenomenon is called the dark flow, and it points toward something unimaginably vast that lies beyond the edge of everything we can see. The discovery, led by scientist Alexander Kashlinsky, came from studying the cosmic microwave background, the faint afterglow of the Big Bang. By observing how this ancient light is subtly shifted as it passes through enormous clusters of galaxies, a technique known as the kinematic Sunyaev-Zeldovich effect, his team could measure the cluster's peculiar motion through space. They found that hundreds of these massive clusters were all streaming toward the same patch of sky, a motion that cannot be explained by the gravitational pull of any known structure, not Laniakea, not the Great Attractor, nothing within our cosmic horizon. This is a current flowing through the ocean of space, and we have no map for what lies upstream. The implications are staggering and deeply controversial. Some researchers argue it must be a systematic error, a flaw in the data. But if it is real, the dark flow suggests that the mass distribution of our universe is not uniform on the grandest scales. Something outside our observable bubble, a region of space-time that inflated away from our own during the universe's first instant, could be exerting a gravitational tug. It is as if we are living on an island, feeling the tide pulled by a massive, unseen continent over the horizon. This would mean our entire cosmos, all 93 billion light-years of it that we can observe, is just a small province in a far grander structure, a multiverse of cosmic domains. What kind of architecture could possibly cast a shadow of gravity across such an impossible void? The dark flow remains one of cosmology's most profound and unsettling mysteries, a ghostly current hinting that the true map of reality is infinitely larger than we ever dared to dream. This ghostly current of the dark flow hints at an architecture beyond our vision, but the universe's hidden blueprints were written even earlier, in a relic sea of nearly massless particles that floods every cubic inch of space. The cosmic neutrino background is a fossilized whisper from just 1 second after the Big Bang, a thermal echo from the universe's fiery infancy. When the cosmos was a seething, opaque soup of particles and energy, neutrinos were born in untold numbers. For a brief moment, they interacted constantly with protons, electrons, and light. But as the universe expanded and cooled in that first second, something profound happened, a moment physicists call decoupling. Suddenly, the density dropped so low that these neutrinos stopped colliding with other matter. They were set free, streaming across the nascent universe without another significant interaction for over 13 billion years. This means 1 trillion of these ancient particles are passing through your body every second, a direct link to the universe's first heartbeat, completely undetected. Nobel laureate Arthur B. McDonald's work on neutrino oscillations revealed that these particles have tiny, non-zero masses, a discovery that confirmed they carry real gravitational influence. This is the key to their cosmic role. While the heavier, sluggish dark matter was forming the first large-scale wrinkles of the web, these ultra-fast neutrinos were acting like a cosmic sandblaster. Their high velocity and sheer abundance meant they could smooth out the smallest clumps of matter by essentially washing over them and dragging material away from the tiniest gravitational wells. This damping effect preferentially suppressed the formation of smaller galaxy clusters, effectively setting a minimum size for the first structures to emerge. You can think of it as the universe using 2 different tools to sculpt itself: a chisel of dark matter to carve the Grand Canyons and filaments, and a fine grit sandpaper of neutrinos to smooth out the small-scale roughness. This fundamental process left a permanent mark on the cosmic microwave background, the later afterglow of the Big Bang. The specific pattern of hot and cold spots we observe in that ancient light was shaped by the phase of acoustic oscillations that these free-streaming neutrinos helped to set. Their presence altered the rhythm of the early universe's pressure waves, and by reading that frozen pattern today, we can infer their properties. So how did these elusive particles help carve the voids and walls we see today? By preventing an overabundance of small, dwarf galaxies and tiny clusters, the cosmic neutrino background ensured that matter was channeled more efficiently into the larger filaments and nodes, ultimately helping to define the stark contrast between the vast, empty voids and the brilliant, dense walls of the cosmic web. This background is not a structure you can point a telescope at, but a thermal memory woven into the gravitational fabric of everything, a fundamental layer of cosmic architecture that guided the placement of all that followed. And if this fossilized sea of particles represents one unseen ingredient, what other primordial relics might be hiding in plain sight, their subtle forces waiting to be uncovered? That primordial sea of neutrinos provided the fine-grained texture for cosmic structure, but the universe itself was still shrouded in a deep, featureless gloom. Then came the first sunrise. After the cosmic dark ages, a new architecture began to form, one not of matter but of pure energy. This was the Reionization Era, a period when the first stars and galaxies ignited, flooding the cosmos with ultraviolet radiation so intense it fundamentally altered the state of the universe. Their light began to eat away at the pervasive fog of neutral hydrogen gas that filled all of space, stripping electrons from their atoms and creating vast, growing bubbles of ionized plasma. Astronomer Abraham Loeb poetically calls this the universe's first sunrise, a dawn that did not happen everywhere at once. Instead, these bubbles flickered to life around the first cosmic overdensities, the densest knots in the dark matter web where the earliest structures were forming. Picture a block of Swiss cheese forming in 3 dimensions, where the solid cheese is the cold, neutral hydrogen fog, and the holes are these brilliant, expanding spheres of searing light and transparent ionized gas. At the heart of each bubble was a source of unimaginable power. The first generation of stars, known as population 3 stars, were likely behemoths, hundreds of times more massive than our Sun. They lived fast and died young, burning with a ferocious blue-white intensity that blasted out torrents of ionizing photons. In some regions, the first supermassive black holes, powering quasars, also contributed, their accretion disks shining with the light of 1 trillion suns. We know this epochal transition occurred because its signature is written in 2 very different kinds of cosmic records. The first is the cosmic microwave background. As the light from the Big Bang's afterglow passed through these newly ionized bubbles, it scattered off the free electrons, imprinting a specific pattern of polarization that our telescopes, like Planck, can detect. This tells us the entire process was largely complete by the time the universe was about 1 billion years old. The second line of evidence comes from looking at the most distant quasars. Their light, traveling for over 13 billion years to reach us, passes through the residual hydrogen of the intergalactic medium. By studying their absorption spectra, astronomers see a gradual clearing of the fog, a forest of absorption lines that slowly thins out the closer we look to the quasars themselves, marking the edge of their own ionizing bubbles. What would the sky have looked like from inside one of these early bubbles? You would not see a uniform, bright glow. The universe would still be predominantly dark, but scattered across the blackness would be these islands of clarity, each one a cosmic beacon. The process was messy and complex, with bubbles growing, merging, and rewiring the very medium of space. This was the first major alteration to the universe's fundamental state, an architectural shift driven entirely by light, a transformation that burned away the final veil and set the stage for the transparent, observable cosmos we call home today. That transparent cosmos, cleared by the first light, reveals structures right on our own cosmic doorstep that remain almost entirely unseen. A vast, spherical shell of frozen worlds is believed to encase our entire solar system, a relic so distant it defines the final frontier of the Sun's gravitational dominion. This is the Oort Cloud, a hypothetical reservoir of trillions of icy planetesimals stretching nearly a light year into the blackness, a structure we have never directly observed but are certain must exist. Its primary architect in our minds was Dutch astronomer Jan Oort, who in the 1950s sought to answer a simple but profound question: where do the long-period comets come from? These are the spectacular, unpredictable visitors that take thousands or even millions of years to complete a single orbit, and their paths appear to originate from every direction in the sky, not from a flat disk like the planets. Oort realized this isotropic distribution pointed to a spherical source, a gigantic cloud of icy remnants left over from the solar system's formation. The evidence is written in the trajectories of these cosmic icebergs. As they swing into the inner solar system, their highly elliptical orbits trace back to this immense, distant shell, a gravitational anchor holding the solar system's frozen history. But what sends these silent objects on their long, plunging journey toward the Sun? They are not simply falling inward. The Oort Cloud is a dynamic structure, constantly stirred by external forces. The gentle but persistent tidal pull of the entire Milky Way galaxy slowly tugs at these distant objects. Even more significant are the rare but powerful gravitational kicks from passing stars. As other suns drift by in their galactic orbits, their gravity can perturb the delicate balance of an object in the Oort Cloud, either flinging it out into interstellar space forever or sending it on a death dive into the inner solar system to become a brilliant comet. On even rarer occasions, the passage of an entire giant molecular cloud through our galactic neighborhood can trigger a comet shower, sending thousands of these icy bodies inward at once. This makes the Oort Cloud not an isolated vault, but an architecture deeply connected to and shaped by our galaxy's movements. Directly observing a single object in the Oort Cloud is one of astronomy's greatest challenges. At such immense distances, these frozen worlds do not reflect enough sunlight for our telescopes to see. They are simply too faint. We estimate its population to be in the trillions, a number so vast it dwarfs the asteroid and Kuiper belts combined. These objects are thought to be primordial mixtures of water ice, frozen gases like ammonia and methane, and rocky dust, the very same building blocks that once coalesced to form the planets. This makes the Oort Cloud a frozen archive, preserving the pristine chemical conditions of the solar system's birth over 4.5 billion years ago. Its very existence and spherical shape are a testament to a violent past, likely sculpted by the gravitational influence of the Sun's birth cluster, a long-vanished family of sibling stars that scattered our system's outer material into this vast halo. So what secrets are locked in this deep freeze? The composition of a pristine Oort Cloud object could tell us exactly where in the protoplanetary disk it formed before being hurled outward, offering a map of the solar system's original construction site. This ghostly halo is the ultimate borderland, a lingering infant structure that binds the fate of our small stellar system to the grand, swirling motions of the Milky Way. And if our Sun holds such a vast, unseen retinue of frozen worlds, what other hidden architectures might surround the countless stars in the darkness around us? That vast, silent halo of frozen worlds is our solar system's most distant architecture, but its calm is an illusion. A river of cosmic wreckage is flowing just outside our galactic doorstep, a colossal ribbon of gas torn from two small galaxies as they are slowly devoured. The Magellanic stream arcs across nearly half the night sky, a faint scar of hydrogen gas that tells a billion-year story of gravitational theft. For decades after its discovery in the 1970s, this stream was a profound puzzle. How could such an immense structure, spanning hundreds of thousands of light-years, simply hang in intergalactic space? The leading theory points to a dramatic dance between our Milky Way and its two largest satellite galaxies, the Large and Small Magellanic Clouds. As these two smaller galaxies swing around our own, they are caught in a gravitational tug-of-war. The Milky Way's immense pull tries to strip them apart, while they also pull on each other during their close encounters. The Magellanic Stream is the visible result, a trail of gas ripped away not just by our galaxy, but by the clouds themselves as they interact. It is tidal debris on a cosmic scale, the shredded outer layers of these galactic visitors. Radio telescopes like the Green Bank telescope have been essential in mapping this structure. They do not see visible light, but instead detect the faint radio whispers emitted by neutral hydrogen atoms. By carefully charting the stream's distribution and measuring the subtle shifts in its radio signal, astronomers can reconstruct its velocity and complex filamentary shape. This map reveals a structure far more intricate than a simple ribbon, with leading arms and trailing tails, suggesting a history of multiple close passes and stripping events. This river of gas is more than just a spectacle. It is a powerful scientific tool. The precise shape and path of the Magellanic Stream are exquisitely sensitive to the gravitational field of the Milky Way's dark matter halo. Think of the stream as a probe, a long, flowing filament that gets tugged and shaped by the unseen mass it passes through. By analyzing its twists and bends, astronomers can weigh our galaxy's dark halo and even map its rough shape, confirming it is not a perfect sphere but a flattened, squashed spheroid. Recent sophisticated simulations have added new layers to this story. They suggest the stream is much older and more massive than we first believed, the product of several distinct episodes of disruption over billions of years. The gas we see today is not from a single event, but from a prolonged and violent relationship. This ongoing destruction offers a stark lesson in cosmic hierarchy. The Magellanic Stream is a temporary architecture, a fleeting monument to a process as old as the universe itself, the consumption of smaller systems by larger ones. The gas in this stream will, over cosmic time, spiral inward and eventually fall into the Milky Way, fueling the birth of new stars in our own galaxy. It is a real-time demonstration of galactic evolution, a visible flow of raw material from the satellites to the dominant center. What does this tell us about the fate of all small galaxies in a giant's grasp? Their identities are not permanent. They are slowly unmade, their substance woven into the grander tapestry of their captor, leaving behind only faint, dissolving trails like ghostly signatures in the void. This ghostly river of gas is not the only debris from our galaxy's violent past. A vast, diffuse cloud of stars envelops the Milky Way, a structure so spread out it was only recently recognized as a coherent entity, challenging our very definition of a galaxy. This is the Virgo Overdensity, a sprawling stellar swarm that may be the mangled remnant of a dwarf galaxy torn apart by our own. Its discovery was a triumph of modern sky surveys. While mapping the heavens with the Sloan Digital Sky Survey, astronomers noticed a curious excess of a specific type of star, the Lyrae variable. These stars act as perfect cosmic mileposts because their intrinsic brightness is known, allowing for precise distance measurements. The data revealed a huge, cloud-like structure of these stars, not in a neat stream, but in a great, messy smudge across the constellation Virgo. The sheer scale of this overdensity is staggering. It spans thousands of light-years, and its total mass may be as much as 1 million suns, rivaling some of the largest dwarf galaxies that orbit our own. The name is slightly misleading, as it is not physically part of the distant Virgo cluster of galaxies. Instead, it simply lies in the same direction, a much closer and more personal structure within our own galactic halo. The dynamics of its formation point to a dramatic history. The leading theory suggests the Virgo overdensity is the result of tidal stripping, the same gravitational process that created the Magellanic Stream, but applied to a galaxy of stars. A small satellite galaxy swinging too close to the Milky Way would have been stretched and shredded by tidal forces. Its stars were pulled away from their original orbits, smeared across a vast volume of space to create this faint, amorphous cloud. We see a similar process happening in real time with the Sagittarius dwarf spheroidal galaxy, which is being unraveled into long, beautiful streams that wrap around our galaxy. But the Virgo overdensity is different. It is more massive and far less structured, appearing more like a splash of stars than a defined ribbon. This has led to a compelling debate. Is it the corpse of a single, large dwarf galaxy? Or is it a superposition, a chance alignment of multiple stellar streams from several smaller victims, all overlapping from our point of view? This faint smudge of starlight represents the ghostly architecture of galactic cannibalism, a visible record of our galaxy's violent assembly history. It forces us to look at the seemingly empty spaces of our galactic halo and wonder what other faint fossils are hiding there, the dissolved remains of ancient galaxies that now form the very foundation of our Milky Way's dominion. Yet even the faintest fossils in our galactic halo are dwarfed by a structure whose very existence seems to defy the rules of the cosmos. The Hercules-Corona Borealis Great Wall is a purported behemoth, a filament of galaxies so colossal that its discovery sent shockwaves through the field of cosmology. This is not a structure seen through a telescope in the traditional sense. Its potential outline was traced using the most violent explosions in the universe, gamma-ray bursts. These brief, unimaginably energetic flashes are thought to mark the deaths of massive stars in distant galaxies. A team of astronomers led by Ist van Horvath noticed that these bursts were not scattered randomly across the sky. Instead, they found a startling clustering in the directions of the constellations Hercules and Corona Borealis, a concentration that suggested an underlying structure of staggering proportions. The data pointed to a wall of galaxies potentially over 10 billion light-years in length, a figure that would make it the single largest known structure in the entire observable universe. The implications of such a discovery are profound, and that is precisely why it remains one of the most hotly debated topics in modern astronomy. The controversy hinges on two critical points: statistical significance and the cosmological principle. The principle states that on sufficiently large scales, the universe should look roughly the same everywhere, a concept known as the horizon of homogeneity. There should be no continents or oceans, just a uniform distribution of matter. A structure as vast as the Hercules-Corona Borealis Great Wall would stretch this principle to its absolute breaking point. It would be like finding a single mountain range that spans an entire planet, a feature so immense it redefines the landscape. Critics of the discovery argue that the clustering of gamma-ray bursts could be an illusion, a statistical fluke born from the way we observe these fleeting events. Our telescopes might have selection biases, missing certain bursts or being more sensitive in specific directions. Perhaps the pattern is not a real wall, but a chance alignment of unrelated galaxies across different distances, a cosmic mirage projected onto the sky. The teams defending the wall's existence counter with increasingly sophisticated analyzers, insisting the clustering is real and significant. They argue that if this structure is confirmed, it would force a dramatic rewrite of our standard model of cosmology. We might need to reconsider the upper limits of how large things can grow, or question whether the forces that shaped the early universe allowed for such titanic wrinkles to form. This debated wall represents the very frontier of our knowledge, a ghostly silhouette on the edge of perception. It forces us to ask a humbling question: are we seeing the outline of a true cosmic continent, or merely the shadow of our own incomplete understanding cast upon the void? This immense debate over distant walls is settled by a profound emptiness right next door. Just beyond our local group of galaxies lies one of the most significant nothings we have ever encountered, the local void. It is not a perfect vacuum, but a region of space so drastically underdense that its gravitational influence is actively shoving our entire galactic neighborhood away. While the titanic Hercules-Corona Borealis wall is debated, the local void's effects are measured and real, a constant, subtle pressure from an abyss. Astronomer R. Brent Tully and his team have meticulously mapped this nearby emptiness using vast galaxy redshift surveys. By measuring the precise distances and velocities of thousands of nearby galaxies, they could trace the contours of this void, revealing its staggering scale at over 100 million light-years across. We reside on its very edge, part of a flattened collection of galaxies called the local sheet that forms one of the void's borders. The physics of this nothingness is counterintuitive. We think of gravity only as a pulling force, but in the context of general relativity, it is the shape of space-time itself. A region with very little matter, like a void, creates a gravitational hill. Imagine a vast, gentle slope in the fabric of the cosmos. Denser regions surrounding this void, rich with galaxies and dark matter, create deeper gravitational valleys. Matter naturally flows downhill, away from the underdense center of the void and toward the surrounding denser areas. So, the local void is not actively pushing us in the way a hand pushes an object. Instead, we are sliding down the cosmic slope away from its center, driven by the greater pull from the denser structures on the other side. A simple analogy is a bubble in a pot of boiling water. The bubble itself is an emptiness, and the surrounding liquid quickly rushes in to fill that space. In the cosmos, the liquid is the collective mass of galaxies, and their collective gravity draws everything away from the void's center. This repulsive effect contributes significantly to our local group's peculiar velocity, that 2 million km/h motion we feel through space. How does nothingness exert such a tangible force? It demonstrates that emptiness is not passive. A void has its own gravitational signature, defined by what is missing. The local void is an active component of our cosmic architecture, a dominant absence that sculpts the flow of galaxies on our doorstep. This constant push from nothingness forces us to reconsider the fundamental forces at play, a delicate cosmic balance where the emptiness itself helps write the rules of motion. Our galaxy's violent history is written in the paths of its stars. A ghostly relic known as the Gaia sausage was discovered not by spotting a shape in the sky, but by tracking the motion of millions of individual suns. Data from the European Space Agency's Gaia Observatory revealed a startling population of stars moving in highly eccentric radial orbits, plunging like pendulums on steep trajectories toward the galactic center and then swinging far out into the halo. These are not the orderly, circular orbits of stars born in the Milky Way. They are the chaotic, plunging paths of an intruder, the scattered remains of a dwarf galaxy that collided with our own around 10 billion years ago. This lost structure was not seen, it was heard in the rhythm of stellar motion, a silent testimony to a catastrophic merger. The stars that form this sausage are distinct in their very essence. They are typically older and metal-poor, meaning they contain fewer heavy elements fused in earlier generations of stars. This chemical fingerprint is a telltale sign of a small, primitive galaxy, one that lived fast, formed its stars quickly, and then was devoured before it could enrich its gas with heavier elements. The sheer number of these stars points to a dramatic event. This was not a minor glancing blow. The Gaia sausage galaxy was massive, perhaps as hefty as 10 billion suns, and its merger contributed a substantial fraction, possibly up to half, of the mass of our Milky Way's stellar halo. The impact of this collision fundamentally reshaped our galaxy. The immense gravitational shockwaves from the merger likely puffed up the thin, primordial disk of the Milky Way, helping to create the thicker disk we see today. It may have even provided the gravitational kick necessary to trigger the formation of the galaxy's central bar, that dense, elongated structure of stars at its heart. This discovery has turned our galaxy from a stately island universe into a cosmic collage, its current form built from the remnants of countless cannibalized siblings. The Gaia sausage is a fossil, but not one of bone and stone. It is a fossilized orbit architecture, a dynamic ghost that reveals how the Milky Way was assembled through violent encounters in its youth. This is the essence of galactic archaeology, a new field where we act as cosmic detectives, sifting through the motions and chemistries of stars to uncover lost chapters of our home galaxy's biography. What other ancient mergers are hiding in plain sight? Their stories waiting to be decoded from the silent dance of the stars. The violent merger of the Oort cluster offers a rare and stunning glimpse of cosmic architecture laid bare. Here, two galaxy clusters have slammed into one another in one of the most energetic events since the Big Bang. Yet the true revelation was not the collision itself, but what it tore apart. Observations from the Chandra X-ray Observatory revealed a spectacular and unexpected sight, a bullet-shaped cloud of superheated gas glowing in X-rays, lagging far behind the galaxies. This was the normal, baryonic matter, the stuff of stars and planets caught in a cosmic traffic jam. The gas, being collisional, interacted strongly, slamming together, slowing down, and heating to millions of degrees. But the galaxies, mostly empty space, sailed right past each other. The real shock came from mapping the cluster's total mass using the phenomenon of gravitational lensing. This technique measures how the cluster's gravity bends light from more distant galaxies, acting as a cosmic scale. The resulting map showed the peak of the mass was not with the brilliant X-ray emitting gas. It was with the galaxies, which themselves did not contain enough visible stars to account for the immense gravitational pull. The mass was in two distinct, invisible clouds that had passed through the collision completely unscathed. This was the direct evidence for dark matter halos, the lost structures that form the true skeletons of galaxy clusters. The dark matter, being collisionless and seemingly immune to the forces that affect normal matter, felt only gravity. It simply followed its trajectory, carrying the galaxies with it and leaving the gas behind. This separation provides a crystal-clear architectural blueprint for the universe. Dark matter forms the stable, underlying scaffold, the framework upon which everything is built. The visible matter, the gas and the stars, is a secondary component that simply falls into the gravitational wells the dark matter creates. It is the steel girder versus the drywall. The bullet cluster makes the invisible visible, offering a snapshot of cosmic construction in its most fundamental form. This natural laboratory tells us something profound about dark matter's nature. It does not interact with itself or with light in any significant way. It only feels gravity. What other cosmic collisions are we yet to witness, where the ghostly framework of the universe reveals itself so plainly against the backdrop of a violent stellar fire? A spherical region of space nearly 330 million light-years across holds almost nothing. This is the Boötes Void, a galactic desert so profoundly empty its discovery in 1981 by astronomer Robert Kirshner and his team sent a ripple of astonishment through the field. Imagine a volume of the universe so vast it could contain thousands of galaxy groups like our own. Yet surveys revealed only a few dozen lonely galaxies scattered within its expanse. The initial observations were startling. How could a structure of this scale, a veritable hole in the cosmic web, even exist? Subsequent, more sensitive mapping confirmed its staggering sparsity, solidifying its title as the Great Nothing. This was not a complete vacuum, but a realm of such extreme underdensity that it forced a re-evaluation of how emptiness itself is woven into the fabric of the cosmos. The handful of galaxies that do call this void home are not randomly placed. They often cling to faint, thread-like filaments that stretch through the emptiness, the last remnants of the cosmic web within the void itself. These isolated islands are known as void galaxies, and their existence is a testament to a different kind of cosmic evolution. Shielded from the violent gravitational interactions and galactic mergers that are common in dense clusters, these galaxies evolve in profound isolation. They are often slower to consume their gas, leading to more relaxed rates of star formation and potentially different morphological structures. Studying a void galaxy is like studying a tree that grew alone in a vast meadow, its shape and growth patterns dictated by a quiet environment, unlike a tree in a dense, competitive forest. The formation of such a colossal void is a natural, though extreme, outcome of the same gravitational physics that built the Great Walls. In the early universe, slight underdensities began to expand faster than their surroundings. As gravity pulled matter into the neighboring filaments and dense knots, it actively drained material away from these central regions, causing the voids to grow and deepen over billions of years. The Boötes Void is not a static hole. It is an actively evolving architecture of absence. a chamber in the cosmic mansion whose defining feature is what is missing. Its sheer scale, however, remains a subtle challenge, pushing the limits of our models for just how large such an empty region can become. This vast desert forces a profound perspective shift. The universe's grand design is carved as deeply by its empty chambers as by its glittering walls. What strange and quiet stories are written in the isolated light of those few galaxies, living their entire cosmic lives in the heart of nothing? Our cosmic horizon is a cage of light, a spherical prison wall we can never breach. This boundary, known as the Hubble Volume, defines the ultimate limit of our observable universe. It is not a physical wall you could touch, but a frontier in time. Its radius is simply the distance light has been able to travel in the 13.8 billion years since the Big Bang. Everything we can possibly see, from the closest star to the most distant galaxy, resides within this immense but finite sphere. The true nature of the universe beyond this horizon is the 17th and most profound lost structure, an architecture that is fundamentally and forever hidden from us. The engine that builds this wall is the expansion of space itself. As the universe stretches, it carries galaxies along with it. The farther away a galaxy is, the faster space between us and it expands. At a certain critical distance, space is stretching so fast that the light from that galaxy, no matter how long it travels, can never reach us. This distance is our Hubble horizon. It is like a runner on a moving treadmill that is accelerating. They can run forever, but they will never reach the end if the belt moves faster than their top speed. This leads to a startling cosmic fate for the galaxies we see today. Due to the accelerating expansion driven by dark energy, distant galaxies are not just moving away, they are eventually crossing this horizon. As a galaxy approaches the Hubble limit, its light is stretched to longer and longer wavelengths, redder and redder, until it is shifted completely into the infrared, then the radio, and finally, its photons become so diluted and stretched that they are fundamentally undetectable. The galaxy does not vanish in a flash, it simply fades from all possible perception, its signal redshifted into oblivion. The future this implies is profoundly lonely. In 1 trillion years, the accelerating expansion will have pushed all galaxies outside our local group beyond the cosmic horizon. The night sky for any future astronomers in the Milky Way will be almost entirely black, the distant cosmos erased. The universe they can observe will contain only the merged stars of the Milky Way and Andromeda, with no evidence that other galaxies ever existed. The Hubble volume will have shrunk to a tiny island in an unimaginably vast sea of nothingness. This horizon is the ultimate informational barrier. It means our entire understanding of the cosmos is based on a single sample, one bubble of reality. We have no way of knowing if the universe beyond is infinite, or if it is structured into an endless fractal of other Hubble volumes, each with its own different laws of physics. Is our universe a lone continent or just one island in an infinite archipelago? The Hubble volume is the final lost structure, a silent, expanding sphere that defines the absolute limit of human knowledge and forever veils the true architecture of all that is. That faint, frozen whisper from the dawn of time is the ultimate cosmic blueprint. The cosmic microwave background is a wall of light, a final scattering surface from when the universe was a mere 380,000 years old. Before this moment, the cosmos was a seething, opaque plasma, far too hot for atoms to form. Light was trapped, constantly bouncing off a dense fog of free electrons and protons. But as expansion cooled the universe, a monumental transition occurred, recombination. Electrons and protons finally combined to form neutral hydrogen atoms, and in that instant the cosmic fog cleared. The light, once imprisoned, was set free to travel across the universe, and we detect that same released light today as a microwave glow that permeates all of space. It is the oldest light we can see, a direct snapshot of the infant universe. This afterglow is not perfectly smooth. When we look at it with exquisitely sensitive instruments, like the European Space Agency's Planck satellite, we see a mottled pattern of tiny temperature variations. These anisotropies are minute, differing by only about 1 part in 100,000, but they are the most important fingerprints in cosmology. Each slightly warmer, denser patch is a region where a little more matter was concentrated, a deeper gravitational well. Each slightly cooler spot marks an underdense region, a shallower well. These ripples are not random. They are the fossilized imprint of those primordial quantum fluctuations, stretched to cosmic proportions by inflation. They are the seeds from which the entire cosmic web would grow. The pattern we see is a two-dimensional projection, a photograph of a three-dimensional reality at a single, ancient moment. It is a fossilized sound wave, capturing the state of the universe when pressure waves from the hot plasma were frozen in place by the sudden clearing of the fog. The characteristic angular size of these frozen ripples acts as a cosmic ruler, allowing us to measure the fundamental geometry of the universe with incredible precision. The data tells us the cosmos is flat or very nearly so, and it gives us a precise inventory of its contents: 27% dark matter, 5% ordinary matter, and 68% dark energy. This relic radiation is the initial condition for everything. The dark matter, already present, immediately began to respond to this blueprint. It felt the pull of those tiny density variations and started to flow into the gravitational wells they defined. Over hundreds of millions of years, this slow, gravitational collapse amplified the contrasts, turning those minute ripples into the vast filaments, clusters, and voids of the cosmic web we observe today. The placement of every galaxy, every supercluster, and every great wall was written in code upon that glowing surface. So how did these minute temperature differences lead to the vast structures we see? They were the universe's first and most fundamental map, the gravitational template that guided all subsequent construction, a lost structure in time that set the destiny for all the architecture to come. Our galaxy's core holds the ghost of a titanic explosion. Two colossal bubbles of high-energy gamma rays balloon out from the Milky Way's center, each stretching 25,000 light-years into the darkness, one above the galactic plane and one below. These are the Fermi Bubbles, a pair of vast, faint structures that went completely unnoticed until the Fermi Gamma Ray Space Telescope mapped the sky in gamma-ray light just over a decade ago. They reveal a cataclysm in our galactic past, an event so powerful it blasted incandescent gas far out into the galactic halo, leaving behind this immense fading scar. The source of this incredible outburst remains one of the most compelling puzzles in galactic astronomy, a lost chapter in the biography of the Milky Way. The leading theories point to two possible culprits, both tied to the galaxy's violent heart. One possibility is a past episode of intense starburst activity, where a wave of supernova exploded in quick succession near the center, their combined shock waves blowing a gigantic bubble in the surrounding gas. The other, more dramatic theory involves our own supermassive black hole, Sagittarius, a star. While it is quiet today, it may have been active millions of years ago, launching a powerful jet of energized particles directly up out of the galactic disk. This jet would have acted like a cosmic blowtorch, inflating these giant lobes over millennia. The bubbles themselves are not empty, they are filled with hot, magnetized gas that is racing outward at millions of kilometers per hour. This gas is what produces the gamma rays we detect through a process called inverse Compton scattering. Essentially, low-energy photons like starlight or the cosmic microwave background collide with the ultra-fast electrons zipping through the bubble. In these collisions, the electrons transfer a tremendous amount of energy to the photons, boosting them into the high-energy gamma ray part of the spectrum. It is a cosmic particle accelerator on a truly galactic scale. The existence of the Fermi Bubbles forces us to rewrite the history of our galaxy. We often think of the Milky Way as a stable, serene spiral, but these structures are a dramatic reminder that it is a dynamic and occasionally violent ecosystem. They represent a form of galactic architecture known as feedback, where the central engine, whether a burst of stars or a hungry black hole, releases so much energy that it profoundly shapes its environment, pushing gas around, quenching star formation, and enriching the halo with heavy elements. This event, though lost to time, is a testament to the cycles of eruption and calm that govern a galaxy's life. What other colossal structures might be hiding in plain sight, their faint light telling stories of ancient fury that shaped the very space we call home? Our own galaxy's brilliant disk casts a long shadow, creating a cosmic blind spot known as the zone of avoidance. This is a broad band across the sky where the dense plane of the Milky Way, with its thick clouds of interstellar dust and countless stars, completely obscures our view of the universe beyond. For centuries, this region was a literal blank spot on our extragalactic maps, a place where optical telescopes could see nothing but the foreground clutter of our own galactic neighborhood. It represented a fundamental limit to our perception, a lost architectural zone where entire superclusters could remain hidden just out of sight. The challenge is immense, like trying to see distant mountains through a dense, luminous fog that is our own galaxy. But astronomers refuse to accept this permanent blindness. They turn to other forms of light, wavelengths that can slip through the cosmic dust where visible light is completely blocked. Infrared surveys, like the 2-micron all-sky survey, peered through the murk because longer infrared wavelengths are less easily scattered by dust grains. Radio telescopes, such as the Very Large Array, listened for the faint whispers of neutral hydrogen gas, the signature of spiral galaxies rotating in the darkness. These techniques have been stunningly successful, peeling back the veil to reveal a hidden cosmos. They have uncovered entire galaxy clusters lurking behind the Milky Way, some of which are directly linked to the gravitational anomaly of the Great Attractor, finally giving form to the unseen mass that pulls us. Every new survey of this zone brings new discoveries, systematically filling in the blank spaces on our map with galaxies and clusters we never knew were there. This ongoing work is a humbling reminder that our perspective is inherently limited and biased. We map the universe from a single, dusty point in a spiral arm, and our entire understanding of cosmic structure is filtered through that vantage point. What truly colossal features, perhaps a wall of galaxies to rival the Sloan Great Wall or a void larger than Boötes, might lie completely unknown within this zone of avoidance, their presence only hinted at by subtle gravitational tugs on the galaxies we can see. This obscured realm remains one of the final frontiers in observational cosmology, a testament to the fact that the most profound discoveries often begin by looking closely at what we have been missing. Far out in the depths of space and time, the universe was building its first true giants. Brilliant beacons, the quasars, began to ignite, and they did not light up at random. They clustered in immense groups, tracing an underlying architecture of staggering proportions. These are the large quasar groups, ancient skeletons of matter that challenge our understanding of the cosmos in its youth. A quasar is the active, blazing core of a distant galaxy, powered by a supermassive black hole feeding on vast amounts of gas. This process makes them the most luminous, steady objects in the universe, visible clear across cosmic time. Because they are so bright, they act as perfect tracers, allowing us to map the distribution of matter when the universe was only a fraction of its current age. The sheer scale of these groups is difficult to comprehend. The huge large quasar group, for instance, is a structure nearly 4 billion light-years across, a concentration of brilliant cores so vast it would take light almost half the age of the Earth just to travel from one end to the other. These are not structures you can see in a single image. Their immense size is only revealed through statistical analysis, by plotting the three-dimensional positions of thousands of these quasars and finding that they cluster together on scales that seem to defy expectation. This clustering points to an incredibly dense environment in the early universe, a massive knot in the primordial dark matter web where galaxies were packed so tightly that their central black holes were constantly fed, lighting them up like a city seen from the air. The timeline of this drama is crucial. The peak of quasar activity occurred when the universe was between 2 and 3 billion years old, a period of intense construction and violence. The light we receive from them today has been traveling for over 10 billion years, offering a direct window into this formative era. Yet their existence in such colossal groups stirs a deep controversy. The cosmological principle, the idea that the universe should be smooth on the largest scales, suggests a theoretical limit to how big structures should be able to grow. The scale of some large quasar groups appears to brush right up against, or even exceed, this homogeneity scale. Do these ancient groupings mean the early universe was fundamentally lumpier than our models predict, or are we seeing a statistical illusion, a chance alignment of separate filaments from our limited perspective? These brilliant beacons have long since vanished. The quasars themselves shut down as their fuel supply was depleted, their host galaxies evolving into the quiet ellipticals and spirals we see today. The giant structure they once outlined has also transformed, its gravitational pull likely having woven a modern supercluster of unimaginable size. The large quasar groups are thus truly lost, their luminous architecture faded into the darkness of time, leaving only a ghostly statistical imprint in our data. They stand as a testament to a more violent, brilliant youth for the cosmos, raising a profound question about the foundations of reality itself. The brilliant quasars and galaxies are merely the glittering nodes in a far vaster, invisible network. The true bulk of normal matter in the universe exists not in stars, but in a ghostly fog of superheated gas, a structure known as the Intergalactic Medium. This is a cosmic web woven from hydrogen and helium so diffuse that a single cubic meter of it might contain only a single atom, yet its total mass dwarfs all the stars in every galaxy combined. This omnipresent ocean is the primary reservoir of the ordinary stuff you are made of, an architecture so tenuous it was lost to science for decades. We cannot see it directly, but we can read its shadow. When the intense beam of light from a distant quasar travels across billions of light years to reach us, it passes through this all-pervading gas. Specific elements in the IgM, like hydrogen, absorb very particular wavelengths of this light. The result is a quasar spectrum, which is not a clean rainbow of color, but a forest of thousands of fine, dark absorption lines. Astronomers call this the Lyman alpha forest, and each line is like a barcode, a unique fingerprint telling us the density, temperature, and distance of a specific filament of gas the light passed through. This forest is our detailed map of the IgM's architecture. The densest thickets of these absorption lines correspond perfectly to the invisible filaments of the dark matter web, where the gas is also pulled into concentrated streams. The sparse, clear patches in the data align with the great cosmic voids, where the gas is thinned to an almost perfect vacuum. This diffuse gas is not a passive bystander, it is the fundamental fuel for galaxy growth. Galaxies are not isolated islands, they are constantly accreting fresh material from these intergalactic filaments, a slow, gravitational rain that feeds star formation. The IGM is also the ultimate recycling plant. When galaxies explode with supernova or blast out gas with powerful quasars, they eject enriched material back into this medium, polluting the pristine hydrogen and helium with heavier elements forged in stellar furnaces. This continuous exchange, the Baryon cycle, means the gas between galaxies today is not the same as it was billions of years ago. It carries the chemical history of cosmic evolution. How does this diffuse gas govern the growth of galaxies? It acts as both a cradle and a graveyard, a dynamic structure that regulates the flow of the universe's normal matter, connecting every galaxy in a single, breathing, cosmic ecosystem. This delicate, filamentary web is the true visible face of the cosmic skeleton, a structure that holds more ordinary matter than anything else, yet remains almost perfectly transparent. The brilliant disk of our Milky Way is cradled by a ghost. An immense, roughly spherical cloud of dark matter envelops every spiral and elliptical galaxy, a massive structure that extends hundreds of thousands of light years beyond the last visible star. This galactic dark matter halo is the true skeleton of our island universe, the primary architectural component that dictates its very form and fate. While we see the glittering stars and glowing gas, this invisible halo contains over 90% of the galaxy's total mass, a dominant presence we can only feel through its gravity. The most compelling evidence for this hidden framework comes from the speed of stars themselves. According to the laws of gravity, stars on the outer edges of a galaxy, far from the bright central bulge, should orbit more slowly, just as Pluto moves more sluggishly around the Sun than Mercury does. But observations tell a different story. Stars orbit at roughly the same constant speed regardless of their distance from the center. This flat rotation curve is a cosmic paradox that can only be resolved if the galaxy is embedded in a vast, massive halo of something that does not emit light, something whose gravitational pull keeps those outer stars whipping around at unexpected velocities. Without this dark matter scaffold, our Milky Way would simply fly apart. We can also map this halo by watching how its gravity bends the light from distant background galaxies, a subtle lensing effect that traces the distribution of mass. Even the motions of small satellite galaxies, like the large and small Magellanic clouds, are dictated by the immense, unseen gravitational well of this dark haze. Their orbits allow us to weigh the halo and confirm its staggering scale. The density of this dark matter is not uniform. Sophisticated computer simulations suggest it follows a specific profile, often modeled as the Navarro-Frenk white profile, where the dark matter is most concentrated at the galaxy's core and gradually thins out with distance. Yet the halo is likely not a smooth, featureless cloud. It may be filled with a rich substructure of smaller dark clumps and streams, the remnants of ancient dwarf galaxies it has consumed, their dark matter halos now swirling within the larger one like faint, dissolving whirlpools. This invisible architecture is the ultimate lost structure, the gravitational glue that has held galaxies together for billions of years. Its true extent and intricate inner workings remain one of the greatest puzzles, the unseen foundation upon which every glittering city of stars is built. The universe's hidden star formation history glows in a color our eyes cannot see. A faint, all-pervading fog of infrared light fills the entire sky, a diffuse shimmer that represents the combined warmth of every dusty, star-forming galaxy throughout cosmic time. This is the cosmic infrared background, a lost structure not of matter but of accumulated energy, the collective architecture of stellar birth that is too faint and blended to be seen as individual points of light. While the cosmic microwave background shows us the universe's infancy, this infrared glow captures its boisterous adolescence, a period of peak star formation hidden behind veils of cosmic dust. Its discovery was a monumental challenge. The Cosmic Background Explorer satellite first detected its subtle signal, but it was later observatories like Spitzer and Herschel that truly mapped this pervasive radiance. They had to peer through the foreground clutter of our own solar system and the Milky Way, meticulously subtracting the light from nearby stars and zodiacal dust to reveal the faint, uniform backdrop from the distant universe. This glow does not come directly from stars. In the dusty nurseries of young galaxies, ultraviolet and optical light from brilliant new stars is absorbed by tiny grains of dust. These dust particles heat up much like sand on a beach warms under the sun, and they re-radiate that captured energy at longer infrared wavelengths. The cosmic infrared background is the sum of all this reprocessed starlight, a fossilized energy output that has been traveling across space for billions of years. It tells us that a vast portion of cosmic star formation was shrouded, hidden from optical telescopes but blazing brightly in the infrared. The fluctuations in this background are its secret language. By analyzing the subtle variations in its intensity across the sky, astronomers can perform a kind of statistical archaeology. They are not seeing individual galaxies, but rather reading the clustered pattern of their combined light, which reveals the timing and intensity of the universe's star-forming peak around 10 billion years ago. This diffuse glow is the only way we can currently probe the properties of the very first galaxies, which are too faint and numerous to be resolved one by one. What dramatic tales of galactic assembly are encoded in this uniform shine? The cosmic infrared background is a humbling reminder that the universe keeps its deepest secrets not always in sharp pictures, but in a collective, whispering light, challenging us to decipher the story of creation from its gentlest echo. But what if every star, every galaxy, and every cosmic void is merely a pattern woven into a fabric that is itself an illusion? The final lost structure takes us to the absolute limit, to a realm where space and time cease to be smooth and continuous. This is the Planck scale foam, the hypothesized quantum texture of reality itself. At scales so small they defy comprehension, the very stage upon which the cosmos plays out may be a chaotic, seething froth. The key to this idea is the Planck length, a distance of about 1/10,000,000th of a trillionth of a trillionth of a centimeter. This is the fundamental pixel size of the universe, a scale so minute that the classical concepts of space and distance break down completely. Here, according to theories like loop quantum gravity and string theory, the fabric of space-time is not smooth. Instead, it is a dynamic foam, constantly bubbling with virtual particles that pop in and out of existence, and potentially riddled with transient wormholes and tiny, ever-changing geometries. In this vision, the smooth, predictable space-time described by Einstein's general relativity is merely an average, a large-scale approximation of an infinitely complex and turbulent quantum foundation. It is the difference between looking at a calm ocean from a great height and realizing that up close, its surface is a churning chaos of individual molecules and waves. We can never directly observe this foam, as any probe energetic enough to resolve such tiny scales would instantly collapse into a black hole. Yet, physicists search for its ghostly signature in the light from the most distant cosmic cataclysms. The idea is that as high-energy photons travel for billions of years across the universe, their journey through this hypothetical foam might cause subtle, cumulative effects. They might arrive at our telescopes slightly scrambled, with their energies altered or their polarizations twisted in a specific way, a faint fingerprint of the turbulent space they traversed. So far, no definitive evidence has been found, leaving the Planck scale foam as the most profound and speculative of all lost structures. It suggests that the universe's hidden architecture is not just made of things in space, but is the very substance of space and time. Is the smooth, continuous reality we experience just a convincing mirage over a foundation of ultimate chaos? This quantum foam represents the final frontier of our search, the base layer of cosmic construction where the architecture of everything truly begins. This grand cosmic map is a testament to what we cannot see. Throughout this journey, we have not been exploring 25 isolated anomalies, but different facets of a single, overwhelming truth. The universe's true architecture is built from darkness and defined by absence. The common thread weaving through dark matter halos, cosmic voids, and phantom flows is the sheer dominance of the unseen. Over 95% of the cosmos is composed of dark matter and dark energy, forces that sculpt and steer everything, yet remain utterly invisible to our eyes and our finest instruments. Our entire reality is a glittering scum on the surface of a deep, dark ocean. Our limitations are not just technological, they are fundamental. We are creatures of light and matter, trying to comprehend a realm dominated by substances that do not interact with light at all. We are temporal beings living in a single, fleeting moment of cosmic time, trying to reconstruct a history that spans billions of years and a future that stretches toward eternal silence. The work of cosmologists like Carlos Frank is so vital because they use supercomputer simulations to build bridges across these chasms of ignorance. They start with the laws of physics and the initial conditions of the Big Bang, and then let a virtual universe evolve. When the structures that emerge in their simulations perfectly match the galaxy clusters and vast voids we see in our telescopes, it gives us confidence that we are on the right track, even if we cannot directly touch the dark matter scaffolding that holds it all together. Each discovery of a lost structure, from the Gaia sausage to the dark flow, does not close a chapter. It simultaneously answers one question and rips open a dozen more, revealing a deeper layer of mystery. Mapping the cosmos has become as much about charting the voids in our knowledge as it is about plotting the positions of galaxies. This is the architecture of ignorance, a positive and active framework that defines the frontiers of human understanding. It is not an empty space, but a fertile ground for the next great discovery. How much of the universe's true design will remain forever beyond our grasp? We may never know, for the greatest hidden structure might be the infinite depth of the unknown itself. These invisible hands have carved a reality far stranger than any fiction. We have journeyed through a cosmos where emptiness pushes and ancient ghosts of galaxies tumble in our halo, where the very space between stars is a fossilized sea of energy. These 25 lost structures are not mere curiosities. They are the fundamental blueprints. The brilliant stars and swirling galaxies we admire are merely the visible ornaments dangling from a vast, dark Christmas tree, their placement and motion dictated by architectures we can only infer. This grand tour reveals a humbling truth. Our understanding of the universe is perpetually, beautifully incomplete. Each mystery we solve, from the nature of dark matter to the source of the dark flow, does not provide a final answer. Instead, it peels back a single layer, unveiling a deeper and more complex puzzle beneath. This is not a failure of science, but its greatest triumph, an endless frontier of discovery. Let this journey leave you with a profound sense of wonder and humility. The universe's greatest designs are its most secretive, written in the language of gravity, woven into the fabric of nothingness itself. The next time you look up at the night sky, see it with new eyes. Know that the true majesty is not just in the pinpricks of light, but in the immense, unseen frameworks that hold them in place, that guide their motions, and that will dictate their ultimate fate. We would love to hear which of these hidden structures captured your imagination the most. Was it the ghostly current of the dark flow, or the cosmic cannibalism of the Gaia sausage? Share your thoughts in the comments below. If unraveling the hidden architecture of the universe fascinates you, be sure to subscribe for more deep dives into the cosmos's greatest mysteries. Join us next time as we continue our exploration into the dark foundations of everything